Hi, I'm Janine Cody, and I wanted to share the talk that we did for the Chromosome 18 Registry and Research Society Family Conference in Baltimore. And I'm recording this for those of you who were not able to attend that amazing conference, and for those of you who, like me, need to hear things more than once for it to stick. So I wanted to talk about sort of the bigger picture. And how does the Chromosome 18 research we've done so far affect your life? And what are we doing or planning to do in the future that will improve the lives of people with Chromosome 18 abnormalities? And I'd like to start by going over the conditions associated with Chromosome 18. So everybody knows which condition their child or their loved one has, but not everybody knows what the other conditions are. And since we're all in this together, I want to make sure everybody knows what each condition is all about. So first is trisomy 18. This is by far the most common of the chromosome 18 conditions. People with trisomy 18 have 3 instead of 2 copies of chromosome 18. And people with trisomy 18 are usually medically fragile, and most, 90%, don't live to see their first birthday. And so the issues that the trisomy families are concerned about are quite different from the issues that the rest of the families are concerned about. And also, there's other organizations very committed to trisomy 18, so that has not been our area of focus. However, we do enjoy the participation of our trisomy 18 families when they choose to join us. And research-wise, we're interested in enrolling in kids with trisomy 18 or adults with trisomy 18, anyone over the age of 4, because we're very interested in the long-term survivors, and their issues are more similar to the issues of the other people with chromosome 18 abnormalities. And it's by far the most common. Then there's 18q-, and with 18q-, you can see here that the person has 1 normal chromosome and then a chromosome with a deletion. 1 copy has a deletion of any size from any position on the long arm, the Q arm of chromosome 18. And this is very rare, occurs in about 1 in 55,000 births. And to make it even more complicated, since I said their deletions can be of any size from any portion, that's not exactly true. There's one place that in the chromosome, pretty small, but we've never found it deleted in anyone. And it's right here in the middle of the long arm, and it's never been deleted in anyone. So that sort of makes it 2 groups. Those with distal, meaning further from the centromere, distal 18q-, and that's 83% of the people who have a chromosome 18q deletion. And then there are the people with deletions in the proximal or proximal closer to the centromere, and that's 17% of the people with 18q deletions. And so they have interstitial deletions somewhere up here in this part of the chromosome. So that's allowed us to separate the information from the 2 groups, because different genes are involved, their issues and their strengths and their weaknesses are quite different. Then there's tetrasomy 18p. This is exceedingly rare. Individuals with tetrasomy 18p have 2 normal copies of chromosome 18, but then they have an extra chromosome, and that extra chromosome is made up of 2 p-arms. So there are 1, 2, 3, 4 p-arms, and hence tetrasomy 18p. And it occurs in about 1 in 625,000 births, so ultra rare. Then there's 18p-, and these individuals have a normal copy of chromosome 18, and their second copy has a deletion of any size from any region of the p-arm or the short arm of chromosome 18. And that occurs about the same frequency as 18q-, of 1 in 56,000 births. And then there's ring 18. So these individuals, again, have a normal copy of chromosome 18, but the second copy forms a ring. And by definition, that means they have missing DNA, they have missing caps from both ends of that chromosome that allow it to form a ring. And that occurs in 1 in 300,000 births. So again, all these are ultra-rare conditions. And we talk about these conditions using various terms. And so I want to clarify those. So someone, like in this example, if you're missing the end of the chromosome, it could be either end, the P or Q arm, it's called a terminal deletion because it's the terminus of the end of the chromosome. But you can also have an interstitial deletion. So in the middle diagram, this person is missing, see this region right here? It's not in this chromosome here. So they have an interstitial deletion, and it's in the distal part of the chromosome, so they have a distal interstitial deletion. Now this individual has a proximal interstitial deletion, the individual on the right. So this region of the normal chromosome, you can see, is missing here. And so they have a proximal interstitial deletion of chromosome 18. So you'll hear those terms used when we talk about syndrome descriptions later on. So the other interesting thing that we've learned is that people can have duplications. And sometimes they're small and sometimes they're large. These are examples of kind of small ones. So here is an instance of an interstitial duplication that's the distal part of 18q. So this region with the little red bracket, you can see there's 2 of them over here. So that person has an interstitial duplication. And in this case, in the case on the right, it's a similar duplication, but the person has a deletion of this part and a duplication of this part. And we're actually finding that to be pretty common. At the break point, there's a little bit of a duplication, and that duplication is inverted. So it's duplicated right there at the end and turned upside down. So it's like a hairpin opened up, sort of a little bit of a duplication. So those are terminal duplications, and those can be very small to very large. The other term that you'll hear described often is mosaicism. And so here's my sort of pathetic interpretation of mosaicism. This is not a honeycomb. These are supposed to be individual cells, let's say from the skin or something. And the blue ones have normal chromosomes. And the yellow ones, in this case, have tetrasomy 18p. And here there are 25 normal cells with normal chromosomes and 5 with tetrasomy 18p. So 5 out of the 30, or 17%, is the level of mosaicism. And so you'll hear more about that as we talk further. Now when we started, this is what molecular analysis was. This was state of the art. And so anything you can do to this picture with scissors, glue, and a copier can happen, and it does happen. It's just very few are compatible with life, compatible with birth. And so those few happen to involve chromosome 18, which makes them rare but quite compatible with life. And this was high-resolution molecular analysis when we started. And hence, because anything can happen, that's why we have such a variety of individuals with chromosome 18 abnormalities, as you'll see when I start showing some of the data. And our goal here is to make the chromosome 18 conditions the first treatable chromosome abnormalities. And by that, we don't mean just reconfigure the person into something they aren't. We want to enable them to have a life of self-sufficiency, just like their siblings with normal chromosomes. So that's our goal, and all the things that we do are focused on that goal. And so what I'd like to do is remind people about how the research we've done has affected your life so far, and how the research we're planning, we hope, will improve your life in the future. So where have we come from? Well, in 1990, when we started, this was the book on chromosome abnormalities. It had 1 page on 18q- and 1 page on 18p-. And the focus was really on diagnostics. How do you recognize somebody with these conditions? So the information was things like small stature, long hands, obnoxious behavior with 18q minus, with 18p minus. It was growth deficiency, wide mouth, alopecia, meaning loss of hair. There wasn't any information here about management. It didn't say why they were short. It didn't say what their behavioral diagnoses were. It didn't say they were hearing impaired. It might say their ears were low set, but it didn't say whether they worked or not. And so our focus has been much more on the management and not how do we recognize, but how can we help people with these chromosome 18 abnormalities. The advice at that time was wait and see. So we're trying to do better than wait and see. And we actually can do a lot better than just wait and see. And at that time, high-resolution molecular analysis looked like this. And so here's a person with a small deletion of 18q. You can pick that out because there's a big red arrow here, but cytogenetic technologists could pick it out quite quickly without the arrow. But the problem here is, yep, that looks like a missing piece of a chromosome. One's shorter than the other, but how much shorter? What genes does this person have that they're missing that everyone else has? You can't quite tell that from this photograph. And here's some examples that sort of had us in some ways confused, but in some ways inspired that there's more to learn here. So at the top, here's the one I showed you before with the missing piece at the end of 18. But here's some other examples of chromosome 18 pairs from other individuals that had findings that didn't quite make sense. So this person looks like they have a very small terminal deletion of 18q. This person had what doesn't look like an 18q deletion at all, but they had delayed myelination and atretic ear canals. So their doctors thought they had 18q minus. They sent them to us. We thought this person had 18q minus, but we did the chromosomes. They did them twice. It looks like 2 normal copies of 18. So what's going on here? Can't quite tell, given this state of the technology. This next person had what looks like a really small deletion of 18q. But they had really significant medical and developmental issues, not consistent with, let's say, this person at the top here, not at all the same. And yet their chromosomes look the same. So something is going on that's different here. And then the bottom one, this individual had a really big deletion of 18q, but they had normal myelination of the brain. And we kind of thought the gene related to normal myelination was right at the end of the chromosome, and they're missing it. So what is going on? So, biology follows rules, just like physics, just like chemistry, and when things don't make sense, it just means there's more to discover. There's something we don't understand. So we needed more precise tools, which we did not invent, but we have employed to use on the chromosome 18 conditions. And thanks to the Human Genome Project, we now can do molecular analysis that can tell us exactly what's going on with these people's chromosomes and why some of these data seem to be confusing. So let me share that with you in a few minutes. But first, where we are now, on the clinical side, we have physician management guides, which are updated as needed. We're about to do some updates to the tetrasomy guide. And these are really intended for physicians. They use medical terms, and they are here summarized right here. So for 18q deletions, and for each one, there's what we're calling the 60-second summary. We jokingly call it, it's a don't panic, it's just a chromosome page. It's one page for somebody who needs just a brief overview of what this is all about. Then there are the subsequent pages give a lot more detail. There's sort of a cover page that's sort of a table of contents. It tells you all the big issues to be concerned about, but you can click on any of these. They're all on the web, and go to a subsidiary page that tells you much more detail, how often that was found or how it was diagnosed, that sort of thing. So it's organized by time. So the things to look for in a newborn, the things to do when someone is first diagnosed, and the referrals to make when they're first diagnosed, and then the list of things to monitor as they get older, to manage annually as they get older. So there's one of these for distal 18q minus, proximal 18q minus, 18p deletions, ring 18, and tetrasomy 18p. And in addition, we have a couple of talks that have been recorded for continuing medical education credit. So a physician or who's interested can watch these and actually get credit for free. And they explain the research that we've done and the management guides and how to use them. But really, more importantly, what this means is we also have guides for creating a personalized syndrome description for the individual with a chromosome 18 abnormality. And we use what we call our gene dosage map. So gene dosage refers to having an abnormal dosage of the number of genes. So a normal dose is 2 copies. So you have an abnormal gene dosage if you have 1 copy of a gene instead of 2, or 3, or 4 instead of 2. So the information we've compiled is in the form of a chromosome map, and every gene is annotated on the map with what is known about how that gene might behave abnormally if it's present in an abnormal dose. Most genes, luckily, 90%, don't have a problem at all when they're present in an abnormal dose. It's only a very small number who do. And so that's why it's important to be able to look up a specific individual's deletion or duplication and see what do we know about the genes in the region. And so we have how-to YouTube videos, and one is how to use the gene dosage map. And then there's another brief one that shows a couple of examples of how the map can be used, and it kind of contrasts 2 different deletions, which I'll do for you here in a minute too. And there's also a description of actually how you create your own syndrome description using the map. So all that information is now available to anybody who wants to use it. And also, just to remind people, on the Chromosome 18 Registry and Research Society website are a series of podcasts that address frequently asked questions. If we start to hear more questions from people or the same question a couple of times, then we'll make more and add to this list. So we welcome your questions. We learn from your questions. So this is on the Chromosome 18 Registry website. In addition, other resources for families that really come from the Chromosome 18 Clinical Research Center but are housed on the Chromosome 18 Registry website are the condition descriptions for each of these, and those are updated by us as we get additional information. But also the Chromosome 18 Registry newsletter that comes out to your email has an article at least once a month on what's going on at the research center, and past issues are archived, so you can see some of the things that we've talked about in the newsletter in the past. And then, of course, there are live broadcasts, some of which involve the research and what's going on in the research. So there's lots of resources for families that did not exist before the Chromosome 18 Registry and the Chromosome 18 Clinical Research Center existed. So, hand in hand with the advances in the clinical are the advances in the molecular, which I alluded to before. So here's the same individual. We saw all their chromosomes in a previous slide, and then we saw the same little cutout of their chromosome 18, and we saw this person had a small deletion of chromosome 18q. Now, with molecular analysis, we can really define that deletion exactly. And so I'm going to show a series of partial screenshots from the University of California, Santa Cruz Genome Browser, which is a website that we have our gene dosage maps on, and we have our clinical molecular data on. I'm sorry, not clinical, but our molecular data on. And here's an example. So here we have the chromosome ideogram across the top. And And below it is the molecular analysis result from this individual. The blue bar shows where their chromosome 18 is intact, and the gap is where their deletion is. So you can see their deletion is exactly in this region. But that really doesn't look a whole lot different from the picture, does it? But it is actually a world of difference. Here we can add views on the website. This view has all the genes on chromosome 18, for example. Each gene is a bar, so you can see. Interestingly, look, there's gaps here where there's no genes, and then there's places where there's a whole bunch of genes real close together. And so you can see the placement of the genes. And in addition, you can zoom in. So here we've zoomed in, and the red box shows the area that we've zoomed in on. And below that is the zoomed in view. And so here's the end of that person's chromosome. Here it comes right here, and here's where it ends. Here are each of the genes this individual has one copy of instead of two. And they're, as you know, they're lined up one after the other. Actually, they're just shown going down the page for readability. And each of these little bars here shows the location of the chromosome with their name off to the left. So we can actually look up every one of these chromosomes. You can, if you're in the genome browser, you can click on any of these and it'll go to another page that tells you all about that information on that gene. So one of the really important things about this that's different from this image, if you took this photograph of a chromosome and we blew it up and blew it up and blew it up so we could really zoom in right on that breakpoint, it would get fuzzier and fuzzier and fuzzier. But with the molecular analysis data shown in the genome browser, we can zoom in and zoom in and zoom in, and we get more and more and more detail. We can zoom in right here and determine exactly what base pairs this person's breakpoint is between. So while at this level on a slide, it kind of doesn't look that much different, the reality is it's dramatically different. It is completely different. And from this, using this methodology, we can learn so much more. So let's look at those people that had us confused before and see what the difference is. This person that looked like it had a really little deletion of 18q, actually, it's not a terminal deletion at all. It's an interstitial deletion. Look, right here. Here's their deletion, and they have the end of the chromosome. So it's not even a terminal deletion. This person who looked like they had 18q minus, they had delayed myelination in intratracheal canals, but the chromosomes look normal under the microscope. Well, in fact, this person has 18q minus. They do have a deletion of 18q, but we learned that they have a duplication of 4q. So they have 3 copies of the end of 4q. And that piece of chromosome just happens to be exactly the same size as the piece of 18q that's missing. So it's in disguise here. This is really 4q, but you can't tell that in this black and white image. So this is what we were able to learn here. And that's why this person has delayed myelination, intratracheal canals, but some other issues that people with 18q minus don't have. That explains it all. This individual looks like they have a small deletion, kind of like the person in the very top picture, but they had much more serious medical issues and behavioral and developmental issues than we would have expected from a small deletion. Well, in fact, they don't have just a small deletion. They have sort of a medium-sized deletion, but they have a duplication, and that's what the red means. So this red piece means they have 3 copies here, but the reality is that piece is flipped over. And so you have this tandem duplication that makes the chromosome look like it's only missing this much when you're looking under the microscope. But in reality, the deletion is bigger, and they have a duplication. So that's why this person was much more seriously affected. And this individual, and I'm not sure you can see this because my little picture's down here on the right, but this person that had normal myelination but had this huge deletion actually has an interstitial deletion. So the molecular analysis helped explain what was confusing to us before. and helps us understand what's going on and sort out which part of the chromosome is responsible for which clinical and behavioral and developmental features. So here's an example. Here, this person has a deletion as shown right here from this base pair to the end of the chromosome. And you can tell that in this image because the red box is around the end of the chromosome. And here's that zoomed in view of what's going on at the end of the chromosome. And at the top are the genes in the region shown across here in navy blue. And so these are from the genome browser site. And then below that are our custom tracks. Here are the genes in the region, just showing the genes that we think have or could have an impact if you have one copy instead of two. And you'll notice not all the genes are shown here. These aren't shown down here because we don't think they have any impact if you have a deletion or a duplication. And they're color-coded by the possible effect. So this is MBP. We think it's responsible for high-frequency sensory hearing loss in more than 50% of people with a deletion of this gene. So it's pink because we think it has an effect in more than 50%. Orange means it has an effect but in less than 50%. There aren't any orange genes in this particular region. Green and purple have to do with risk factors. So they have a very low probability, but still a probability of causing a problem. Below that, all these long bars, these are the regions we've associated with various medical or developmental issues. We don't know which gene it is, but we've got it narrowed down to a region. And we're trying to figure out, at this point, which gene is responsible. And like I said, orange means a less than 50% chance, and pink means more than 50% chance. So here's delayed myelination and growth hormone deficiency, a cleft abnormality. Vertical talus is less than 50%, kidney malformations, they're less than 50%. So you can look up exactly someone's coordinates of their deletion and determine what genes are in the region, what we know about those genes when you have abnormal gene dosage, and what are the phenotypes, the conditions that we've associated with the region, but we don't know exactly which gene yet. So actually, there is someone with the same deletion, and this person actually has an IQ of 120. They are hearing impaired. They have atretic ear canals. They have a foot deformity, and they're growth hormone deficient. They have dysmyelination, and they have executive function difficulties, meaning they sort of have trouble performing as an adult, organizing their lives, getting things done in a timely manner, in a logical way, that sort of thing. So they still require some supervision, but doing pretty well. So here's another person who has an interstitial deletion of 18q. So you can see that here's the coordinates of this person's deletion. So these are the coordinates you would put in the gene dosage map, and you would get a little red box right there with this zoomed in view below. Again, here are all the genes in the region, and here are the ones color-coded. And of course, importantly, here's the TCF4 gene. Here's the gene shown here. Here is our color-coded with a more than 50% chance of having an effect of this gene, and it causes the clinical phenotype of Pitt-Hopkins syndrome. Actually, if you click on any of these in our gene dosage map, it'll take you to a second page which will tell you more about it, what we think and why we think it, and the references we use to get there. So that's this region, and again, you can see there's quite a few genes we think really don't have any effect when you have a deletion in this region, and there is one phenotype that's seen less than 50% of the time if you have a deletion of this region, and it's a Dandy-Walker variant, which is a brain malformation. And in contrast, these two individuals whose deletions I'm showing you have deletions of about the same size. And so in contrast, this person's development at 3 years was that of about a 6-month-old. At 10 years, they were still not walking, talking, and were not toilet trained. They fit the diagnostic criteria for autism. They had the facial features of Pitt-Hopkins syndrome. But really importantly for this example, they had normal hearing and normal ear canals. They were not growth hormone deficient, and they had normal myelination. All these last three things here, those are associated with a deletion of the end of the chromosome, not a deletion of this region of the chromosome. So this is why the molecular analysis can be so helpful. You might get a really long list of potential issues with an 18q deletion, a distal 18q deletion. Both of these are distal 18q. And from the molecular analysis, we can learn pretty quickly which from that really long list of potential problems applies and which don't apply. And that's what's really helpful as our families go through what's really not a diagnostic odyssey, because the diagnosis comes pretty quickly and pretty easily. It's the management odyssey of what applies to them and what doesn't, and what do we do about it. And that's what we're all about. So just make sure the people with 18p- don't feel left out. The gene dosage map includes all of the chromosome. And here is a view. Let's see, the red box is around the whole p-arm, so the view below is the whole p-arm. And here are the genes that we think have an impact. You'll notice you can hardly see any pink ones, so there's not any that cause a problem in more than 50%. Most of these actually are purple, meaning conditional, meaning you need to have a change on another chromosome in addition, or on this, or a mutation in the same gene on your normal chromosome in order to have that particular problem. And these are the phenotypes associated with the region, or the phenotype regions. And you'll see they're pretty big. And that's really because we don't have anybody with an interstitial deletion of 18p that helps us make these into small regions. But doesn't mean we're not working on it. We're still interested in, and actually have several projects going on to try to identify some of these genes associated with these key phenotypes for 18p-. And in order to do that, and to establish, all of this is about establishing standards of care. We do that because we have a centralized repository. So this is one place where everybody's clinical information comes. We do the clinical evaluations when we have funding to do them. We collect all the medical records all the time. If you haven't sent yours in recently, please send us some more. And we do surveys and questionnaires. We try to follow people for their whole life to determine how they're doing in life, how they're doing developmentally, how they're doing medically. Are things changing? Are they getting worse? Are new problems cropping up we didn't know about before? And of course, we also do all the molecular analysis in-house. So we can compare one person's data to another. And just to show some of the complexity, if you remember way back, I showed that slide with the copier, the scissors, and the glue, and said anything that can happen does happen. And so here's just an example of the complexity that we see. And when we're trying to understand what genes do what, we have to be very aware of the complexity. So because 18p- is less complicated, I'm going to show an example with 18p-. So here we have 127 people enrolled with 18p deletions. 52 of them have a deletion of the entire short arm of chromosome 18. But within that group of 52, 17 have another chromosome involved. Except that other chromosome that is taking the position of the p-arm does not have a deletion of its own. So we need to know there's another chromosome involved, but we also need to know that it probably doesn't impact the 18p features. On the other hand, there are 6 individuals who have another chromosome involved, but it does have a deletion or duplication on that other chromosome. So they're not the typical 18p- individual. And then there's one person who has a duplication at their breakpoint. Like I showed you, the red that's right at the end. So this terminal duplication. Now, there's 65 individuals who have smaller deletions. So they don't have the whole PR missing. They have some smaller portion of the PR missing. And 11 of them have another chromosome involved, but no deletion or duplication on that other chromosome. 6 have another chromosome involved where there is another deletion or duplication. And 2 of those have a duplication at the breakpoint. So all of these things are things we need to know as we try to make correlations between the chromosome deletion or duplication and their clinical features. So we have, to date, or as of the end of June, we have 650 individuals enrolled in the Chromosome 18 Clinical Research Center. Considering that these are ultra-rare conditions, this is a phenomenally large group of people. But because there's so much variability, we can never enroll enough. Because so many people are unique and have unique deletions that we really need a large number of people in order to sort this all out. And those individuals really come from all over the world, principally North America, but pretty much every continent except for Antarctica is represented here. And it's usually an issue of being able to send blood to us. And but we are happy to attempt to enroll anybody from anywhere. So hopefully this gives you a little insight into how the research has affected your life so far. And now I'd like to talk about how research is going to improve your lives even more in the future, how we're going to be able to provide even more information. So some of that comes from clinical observation. So by that I mean we know there's various issues that people have and we want to know more about it. So we just finished a Caesar survey, for example. We're all about natural history and long-term follow-up. We do questionnaires all the time on how people are doing, and we'll continue to do those. That includes everyone. For 18p-, we were interested or concerned about potential inflammation and autoimmune disease. So last year at the conference, we drew blood and did CRP levels. It's an indication, very nonspecific, of inflammation to see if that gave us any hints of unappreciated inflammation. And we found that pretty much everyone was normal. That we didn't get very far with that, but it was a cheap test. It was easy to do at the conference, and it gave us a little more data. With the tetrasomy group, we have a paper that's just submitted on low bone mineral density that was followed up by questionnaires and gathering data from families. We're also interested in sleep, really in everyone, sleep issues, and working on remote assessments, and we're interested in anxiety and depression. So all of these came about, these projects, through clinical observation. Our latest one on tetrasomy 18p is on constipation. And these are observations from the families that are prompting us to emphasize the magnitude of this issue in the management guides, in the syndrome descriptions, and to look into it more carefully to see if there's some neurogenic cause. So these are new investigations or ongoing investigations prompted by clinical issues that we've observed or that families, which is usually the case, bring up to us. And so we want your questions, we want your concerns, because that's how we move forward and make life better for all of you. But on the flip side of that, as we learn more about the genes on chromosome 18, and what they do and how they may impact someone with a deletion or a duplication, sometimes that gives us clues to look for things we hadn't thought of or hadn't appreciated before. And so we are trying to improve what we know and increase what we know based on some of the genes. So, for example, SMCHD1 on 18p is associated with a type of muscular dystrophy, And last year at the conference, we drew blood on people with 18P, and we did CPK levels to see if there was some subclinical indication of this muscular dystrophy, which is an adult onset condition. And we did not find any indication of that. But still looking, because we still think that people with 18P should be at risk for this. This year at the conference, we did video interviews. And those shortly, iPad will be going out for people to do those interviews at home as well as we collect more data. So we're on the lookout for this issue. And if anyone displays some of the symptoms, we're going to be on top of it before that person would typically have gone to the doctor with issues. So hopefully there are things we can do with early intervention and early identification. Likewise, AFG3L2 gene is involved in spinal cerebellar ataxia type 28. It's extremely rare, and so there's not a lot known about it, but what we have noticed is that people with 18P seem to have, as they become young adults, speech that's harder and harder to understand. That could be related to a symptom of this condition, and so that prompted our video evaluations that we did at the conference, and we'll be sending those out to have people do those on our iPad and send them back to us as the year progresses. Again, AMLin2 gene prompted us to look for clotting and bleeding issues in people with 18P minus and tetrasomy 18P. And so a paper has been submitted about that because they don't quite have normal bleeding and clotting issues. And so we're trying to understand that and how that may impact them. Likewise, with 18Q minus, the MC4R gene is believed to cause excessive obesity if you have a deletion of one copy of that gene. We now twice, maybe 15 years ago, and then recently looked at people with deletions of that gene and people with deletions of 18Q who didn't have deletions of that gene, and we do not see a weight change difference in those two groups. And that paper that has that data in it, I believe, is submitted or in press. Likewise, TCF4, as we know more about TCF4 and Pitt-Hopkins syndrome, we're looking into the issues, especially hyperventilation related to that, and how we can assess that remotely using something like a Fitbit sort of iWatch kind of device. So those are just a few of the things that we're working on that are prompted by knowledge of the genes on chromosome 18. So how do we go about finding those key genes? Because as you saw, we've got all these phenotype regions where we don't know exactly which gene is causing the particular phenotype, the particular issue. And so here's a diagram that you've probably seen over and over for the last 15 years. Kind of put it on its side so it correlates a little more with the molecular analysis view you've been seeing. But here's the basic idea. It's pretty straightforward. We have here 4 people, all in this case, different deletions of 18Q. And here's their phenotype, their clinical feature. It could be behavioral, it could be physical, it could be most anything. And in this case, subject 1 has phenotype A, subject 2 has A, B, and C, 3 has B and C, and 4 just has C. And when we correlate those and we say, okay, let's look at everybody with phenotype A. That's these 2 people. What's the one region they have missing in common? It's right here. So we would say this region of the chromosome probably has a gene that causes or contributes to phenotype A. Likewise, you could say phenotype C. These 3 people have phenotype C. So what's the one region they all have missing in common? Well, this is the smallest region right here. So we would say this is a region and has a gene that could cause phenotype C. And so that's how we get the phenotype regions in the first place. And what that requires is 3 things. It requires an awful lot of people with a lot of different breakpoints in order to make these regions really small. You saw with 18P, we don't have anyone with an interstitial deletion, and that's why those regions are big. We don't have anyone that kind of cuts off the region like they would like this person defines the lower limit of this region for phenotype A. The other thing we also need is really good phenotypes. Short is not a good phenotype. Growth hormone deficient or bone dysplasia or those are phenotypes that we can understand, and so that we can investigate further. And so we've been really focused on clinical investigation of exactly what the issues are. And then the third thing is we really have to have high-resolution molecular analysis to be able to tell this person's deletion is different from this person's deletion. And you've already seen evidence of that. So those are the three things we need, the three things we employ. A lot of people, really good genotypes and really good phenotypes in order to do what we do. And so here's the phenotype map for the whole chromosome. Here you can see the red boxes around the whole chromosome, so this is the whole chromosome view. And these are all the regions we've identified associated with different behavioral or physical features, but we don't know which gene yet. And we're hoping when we understand which gene, that will give us some insight into the molecular basis and give us insight into how it could be treated. And as you can see, they're color-coded. Remember, pink causes, if you have a deletion of this region, you have more than a 50% chance of having this condition. If the orange ones, it's less than 50% chance. And these two red regions are the regions nobody has deleted. So here's one of our strategies. And we have a small pilot project grant to start doing this. So this strategy it involves people with Mosaicism for their chromosome 18 condition. And so here's a person with Mosaicism. Now this is just bad clip art. It's not like one half of their body has 18q minus and one half is normal. The Mosaicism, the cells are interspersed throughout the body, more like the picture I showed you, the honeycomb sort of picture earlier. And so what we can do, it's most easily done with skin cells, is to take a sample from this person, and then in the lab we can separate the cells with normal chromosomes from the cells with 18q minus. And then, oops, I should back up a little. I'm jumping ahead. So then the really important thing is everything about the genetics of these two cells is identical except for the deletion of 18q. They're completely the same except for the deletion. So we can compare these and learn how these cells behave different from normal, and with regard to all kinds of things. And these cells can be differentiated into neurons, for example, and look at how these neurons are different in how they behave, what their biochemistry is, their physiology is, and how they're different. So then what we can do is, if we're interested in, let's say, a neurologic phenotype, a phenotype in brain cells, let's say, these can be differentiated into brain cells, and then we take the normal cell and we cut out one gene, just one, not all the 18q minus, and then we say, what is this cell like? It's not like the normal cell anymore. In this case, we took out one gene and it behaves just the same way the 18q minus cell behaved. So, aha, this is a key gene. Yay! What do we do next? We delete that one gene in a mouse and see if, in fact, the mouse has a similar feature, whether it's anatomical or physiological or behavioral, to what we see in someone with 18q minus. And then the next step, if it, in fact, has the same outcome in the whole organism, then there are huge libraries. There's whole core facilities here that are able to take lots and lots and lots of different chemicals, some already approved for use in humans, but they're not on the market because they didn't fix the problem they were supposed to fix, or didn't fix it better than the currently available drug. But they've been used in humans and they're not toxic. And so there's thousands of these drugs who have failed clinical trials in the end. And we can see which of these now make this cell with a deletion of one gene on 18q, which can make it like the normal cell. And that's the path to drug development. I have skipped like a lot of steps in this process, but this is the basic idea. This is doable. We have a plan. We have the ability to execute this plan. We don't have the funding to execute this plan. So that's what we're working on now. And that's why you're always asked to participate in a Starfish Dash or something of that sort to help us move this along faster. And this example may be on 18q-, but this could apply to tetrasomy 18p, 18p-, whatever. Some of the top projects on the list that we don't have funding for that we think are really important to do are clinical evaluations of adults with 18p-. The only people we've seen with 18p- were when they were children. We need to know more about these adult onset conditions and the potential for those. We're also interested in the dysmyelination gene identification. That's the project we have some pilot money for that's about to run out to identify the key gene that causes dysmyelination of the central nervous system. We are trying to develop an assay for platelet function, which is the bleeding clotting issue in people with tetrasomy 18p and 18p-. We need some funding to do that. Also remote assessments, like I said, being Fitbit sort of assessments. We need help, collaborator help with that. Mouse models for the behavioral genes. And I didn't talk about this, but we have a project where we deleted one of the genes on 18q and are monitoring the mice for behavior changes, which they do have, and because they correlate with people with 18q. So we need to be able to do additional studies on that and follow up with potential drugs, etc., drugs that would help that problem. And we need to catch up on microarray analysis. Now, in the past couple of years at the conference, we've had handouts that we shared at each syndrome breakout group. And after a couple of years, most of what's in those handouts doesn't really change. And so some people have seen them year after year, and some people are at their first conference. So what we did different this year was to send these out to all the conference attendees, send out this link. And I recorded a YouTube video just like this to go with each of these. So you can go to our website and you can print out the PDF of the handout for each of these conditions. And then you can go to YouTube and see the video and have me talk you through it, each one of them. So that's this year's sort of syndrome description, so it's more specific to each condition. And just a reminder, our goal is to make the chromosome 18 conditions the first treatable chromosome abnormalities. And like I said, that means self-sufficiency. It means not have to worry about what's going to happen to your child with a chromosome 18 problem when you're gone, not having to have a trust fund, not having to worry about all those things any more than you worry about those things for your kids with typical chromosomes, which can be a lot of worry, but it's not the same. And, you know, after all, it's just biology. So we can figure this out. We just have to do it. And in order to do that, we have a big team that I'd like to acknowledge here. Many of these people have been on this list for decades now who have been helping us and are real experts on the chromosome 18 conditions. But you'll notice at the bottom of the list, some of these are much more specific. So we now have an expert on bone health, platelet function, as well as mouse behavior, mouse electrophysiology, and cell-based assays. And we've recently started collaborating with a speech therapist. So we have a long list of collaborators, and trying to keep those people moving forward and to assist them in their work, because they're virtually all volunteer at this point in time. We do have a staff of people who have been with us a very long time. The newest person, I think, has been with us 11 years, so this is someone very, very committed to all of you and to making life better for you. I hope you appreciate that commitment that they've made with their lives on your behalf. We have administrative help in Gloria and Linda. On the research side, the research but not lab side, there's Annis Hill, who I think everybody knows. She's the main point of contact. Mimi Hassi, who you probably don't know, but Mimi is a foreign-trained medical graduate, and she uses all that knowledge to abstract all the medical records and help us do searches when somebody says, does anybody else with tetrasomy 18p have XYZ? We look it up and we can find that out. And then when we realize, oh, 3 or 4 people have that, then we investigate it further. So Mimi helps us with that. David Rupert is our technical expert for computers and database issues and anything else related to software or hardware. Bridget Swallow is our psychometrist, so she sends out the surveys mostly related to behavior issues and life and work sort of development issues. And Courtney Siebold is our genetic counselor, who answers questions, explains things. She's the one responsible for most of the articles in the newsletter. She's a great writer, and so many of you correspond with her. Just to remind you, our core activities, which you've probably figured out at this point by listening to this, we do have a DNA and cell bank. We collect all the medical records, abstract them, and summarize those, and they're in our database. And most of them are scanned, so we still have the original documents. We do lots of surveys, that's Bridget, the DNA analysis. We do clinical evaluations, and ultimately turn that around for information for families, because that's really why we do all this. That's what it's all about. The people that I want to make sure you know who they are, because these are the people you'll see at the conference or who you correspond with. Again, Courtney Siebold is there to answer most of the questions. Bridget will be sending surveys. Bridget's the one who does the medication list that is really, really helpful for us to help keep up with what's going on. And Anna Sales, the main point of contact. That's who you contact to enroll. She collects pictures and the medical records and sends them off. And if you have a question for any investigator in particular, or a very specific question, then she'll send that on to the person who needs to answer the question, myself, Dr. Hale, Dr. Brooks, Dr. Atkinson, whoever. And most importantly, she will bug us until we answer you, because we get so many emails, and when it's, oh, I'm going to have to think about this when I have time and then answer it when I have time, those are the emails that you tend to forget, and so she won't let us forget them. So Anna's Hill is key for that. In addition, we have appreciated that we have a lot of people, a lot of clinicians who know a lot about the chromosome 18 abnormalities. And we don't have funding at the moment to bring people in for research studies, but that doesn't mean you can't see these individuals. It's just not as part of the research study. However, if you're already enrolled in the research, that means we have your medical records. That means you've made some commitment to us, and we're willing to try to do whatever we can do to help. And so Annis will help research participants come and see our clinicians for a private patient sort of visit. That means you've got to pay for the travel and the hotel, and you or your insurance has to pay for all the doctor appointments or medical tests or anything. But we can help you arrange it. So the way you do that is you contact Annis with possible dates and what your specific concerns are. And update the medical records. And we'll look at the medical records, and oftentimes we'll say, you know, we really think you need to see Dr. So-and-so. And we've had a few families say, oh, no, I've got a great doctor who does that. I don't need to see them. And we say, yes, you do. And more often than not, in fact, in every one of those cases, I believe, those families have come back and said, thank you so much for having us see this doctor. We learned so much. We had no idea. And so we'll help you see the right people. But Annis will also get your health insurance information, and she'll help get those visits close together. She knows the clinic staff and the appointment people, and she'll try to get all those appointments within a couple of days, which you could probably never do on your own. But this is fundamentally different than a research study because we need to have you fill out the release of information form so that we can get the information back from the doctors. So what's different is that your insurance has to pay for all the medical tests and for the evaluations, and you have to pay for your travel and housing. I'm sorry, I wish we had the funding for it, but we just don't. And the research center doesn't automatically get any of the information, so you have to fill out the release of information, because this is a private doctor appointment with them, just as if you would see any doctor in your own town. You need to get pre-authorization just like you would normally. So all those same things need to happen. It's just we'll help you get the appointment in a timely way with the right people. And just as if in any other doctor appointment, the reports will go back to your doctor. They won't go to you directly, and they won't come to us. They'll go to your doctor, just like any other medical specialty report that you would get. So as a reminder of why some things aren't happening as fast anymore as you would like to see, as we would like to see, just to make a reality check for everybody. 10 years ago, it represents the people we had working with us. The light blue part of each of these individuals is the part they had dedicated to chromosome 18. This is me, Dr. Hale, with half time. Various other people had half of their time dedicated to this project. Here are the staff. Some people worked on multiple projects, but had significant time dedicated to this. This is where we are now. I'm the only faculty member with any dedicated time to this. So it's really hard to get other people who have overcommitted for other things and whose time is paid for by other projects to get them to help. It takes lots of bugging, and things don't go as fast as we'd like. Means they still want to, they just don't always have the time to do it. The staff is also reduced not only in number. We've had a couple of people who have left, not because we laid them off, because family situations have taken them to other cities, but we've also have to share some of our staff with other people who have funding and need their expertise. So we have fewer staff and fewer faculty able to work on these projects. So I hope this answers the question about how the research has affected your life so far, and about how the research yet to come has promise for helping your life in the future. And just a reminder, if we didn't do this, it wouldn't get done. Nobody else is doing this work. So we need to keep the work up. We need to keep it alive. And there's so much more we could do if we had the funding to do it. In this age of anti-intellectualism and anti-truth, NIH and others are, in the government, are decreasing their funding, especially for things that never were popular, I guess scientifically popular, which means that in their age of reduced funding in general, investigators all over the world are looking more to philanthropy and foundations for support. So support from those is even getting harder to get, because they have so many, foundations have more applicants than they've ever had before. So it's really going to take a grassroots effort on our part to keep this going, because there's so much more we could do, and so many more ways that we could help improve the lives of people with chromosome 18 abnormalities. And again, if you have questions, here's the email address for Annis Hill. Email her. She'll get your email to whoever. Sometimes she'll say, oh, this is complicated, let me call you back, and you can have a phone conversation. We appreciate your support. We appreciate your questions and all the effort that you put into making life better for people with chromosome 18 abnormalities. So thank you so much. Have a great day.